Hey students, it's Jennifer Hawksworth here, and we're continuing with Chapter 4 on multiple integration. And in this video, we're going to go over Section 4.4, which covers applications of double integrals. So these are our goals for this section. All of them are application related, and they make use of the double integral. So the first thing we're going to do is find the mass of a planar lamina using a double integral. Then we're going to go ahead and find the moments of the planar lamina using double integrals, and then finally finish up the section by finding center of mass, again using double integrals. So the mass of a planar lamina, so basically a thin flat plate of material of constant basically uniform density rho is called a planar lamina. Density is normally expressed as mass per unit volume, so for example grams per cubic centimeter. For a planar lamina, however, density is mass per unit of surface area. So you can think of this here, this equation. Mass is your density times the area. We're going to extend the definition of the term lamina to include thin plates of variable density in this section. This is going to make the problem a little more interesting. So double integrals can be used to find the mass of a lamina of variable density, where the density at an ordered pair x, y on that lamina is given by a density function rho. All right, so we're gonna do some work to kind of get to the formula that we're gonna be using. So consider a lamina with constant density, right? Mass is equal to rho times area, right? That's what I stated on the last slide. We're gonna rewrite that so that you get an integral. So think of it this way. Rho is still rho, that's fine. But this area, I'm going to rewrite it as an integral, a definite integral, much like you would have seen in Calc 1 or the beginning of Calc 2. So put a little picture here. Right here you have a couple curves. X, this is y. This is function f of x. This is function g of x. You're going from a to b. You're finding this area here. So basically, you have dx. X is going from a to b, right? A to b. And your integrand, the part inside here, that would be the top of the curve, top curve minus the bottom curve, right? Minus, top minus bottom. That's how we did it. So you get a definite integral. Okay, then you're going to rewrite that definite integral as a double integral. You can do this as follows. Basically, your outside, where'd my pen go? There you are. The dx is the outside integral, your outside differential, right? X is going from a to b. This part here, maybe I need this back. This was f, this was g, right? A to b. So x is going from a to b. Y is basically between these two curves, f and g. So f and g become your limits of integration, and you just have like 1 dy. Right? So that's how we can write a single integral as a double integral. Now, once we have that double integral, rho can go inside of all those integrals, right? Both of them. So it's inside there now. And then you can replace rho with basically a variable rho. So rho can be a function in terms of both x and y now once it's inside that double integral. And instead of writing the limits, just write region R there. And dy dx becomes your dA. So basically, we're in this scratch work on the slide here, kind of working backwards, right? We were in section 4.1. When we did these problems, we had double integral, and we would work to get a single integral, basically. Here I'm working backwards. I'm starting with a single integral, and I'm rewriting it to get a double integral. Hopefully that explanation makes sense. Now, this part right here is what I'm going to use in the next slide for my definition. All right, definition for the mass of a planar lamina of variable density. If rho is a continuous density function on the lamina corresponding to the plane region R, then the mass m of that lamina is given by this double integral. And this is for a variable density. So rho here is a function in terms of both x and y. All right, so we're going to use this in the first example. So example 1, we want to find the mass of a lamina bounded by the graphs of the equations y equals x squared, y equals 0, x equals 2, and we're doing this for density function rho equals k times x times y. All right, so we're going to start by maybe doing a little sketch. Okay, so I want to know what my lamina looks like. So it's bounded by x equals, or y equals x squared, y equals 0, and x equals 2. All right, so y equals 0 is just the x-axis, then you have your parabola shape of x squared, and then you have this vertical, this really poorly drawn, but it's supposed to be a vertical line at x equals 2. So that's your lamina. Right, so that's a 4 there. So this is the ordered pair 2 comma 4, this point right here. All right, so we want to find the mass, and our density function is a constant k, x times y. All right, so mass m is going to be given by the double integral over the region for the density function dA. All right, so I'm going to replace this with k x y, and then the dA I'm going to write as dy dx. I'm going to put it in that order. So y is between 0 and this curve here, x squared, and x is between 0 and 2. All right, so I set up my limits of integration. Then once I have that, I can go ahead and actually integrate. All right, so I'm going to integrate this here with respect to y, so I get 1/2 k x y squared, and we're going from 0 to x squared dx. All right, I go ahead and plug in the upper limit x squared for the for the y, and then you would subtract plug in 0 for the y, which is just going to give you 0. So you're left with this, which we're going to simplify on the next slide. So we're still going from 0 to 2. We have a k of 1/2, and an x, and an x squared, which is a force, right? Yeah, and a dx. All right, so rewrite this one more time. I don't know if I want to just put it like that. Okay, so 1/2 k x to the 5th, and then integrate with respect to x. So you get 1/12 k x to the 6th. We're going from 0 to 2. Plug in the upper limit 2. I'm not going to worry about the bottom limit 0 because it's just 0. And then simplifying this, we will get 16 thirds k, and you can check that. So this is the math for that lamina. Okay, moments and center of mass. So I need to talk about the moments before we can calculate center of mass. And what we're going to do for the next couple examples, we're going to basically use the same lamina that we set up in the first example. So the physical significance of the center of mass is that the lamina behaves as if its entire mass is concentrated at its center of mass. So if you have this lamina here, and where it's darker, the shading is darker, that's where it's denser, then basically this right here is the center of mass, and you can basically balance that lamina at that point. So it's not going to rotate in any direction. So it won't be rotating at all about the y-axis or about the x-axis in like either of those directions. It will just be balanced there. All right, so moments, and this is how we will use them, how we will denote them, m sub x and m sub y, of the entire lamina about the x and y axis respectively are needed to find the center of mass. So moments are the tendency for the lamina to rotate about the axis. So go back to this picture for a second. Right, if it's balanced here, there's like a pencil that the lamina is balanced on, then it's not going to rotate about the y, right? But if you move, let's say you move this pencil so it's over here, then it's going to start tipping in that direction, right? So we need to calculate the moments, basically, so that we can figure out what the center of mass is. All right, so let's go back over here. Okay, in each case, the moment is going to be the product of the mass times a distance. All right, so here we have the moment about the x, here we have the moment about the y. So the moment about the x-axis is given by a double integral, where here you have your mass like we did before, so your density function times the area, that's your mass, your double integral over the region, except the only thing that's really new is this extra factor of y. Y is the distance from the x-axis. Okay, so the moment about the y-axis, m sub y, is given by that same double integral over the region. You still have your mass here, density times area, but in this case you have x here, which is the distance from the y-axis. All right, now these moments, m sub x and m sub y of a lamina, are sometimes called the first moments. Oops, I didn't mean to actually cross that out. I kind of just want to underline that. But these are called the first moments about the x and y axis. All right, so moments of a variable density planar lamina. We're going to let, oops, I'm missing something. Let here, rho, there should be a rho in there, I got to fix that, be a continuous density function on the planar lamina R. The moments of mass with respect to the x and y axis are given by these here. So we're going to use both of these in the next example. So for example 2, we're still working with that same lamina, same equation, same density function. We just want to find the moments of mass. All right, so I'm going to go over here to do it. Example 2. All right, so you put down the equation first. All right, and we're still working with this thing here. Oops. All right, so my limits are the same as they were from example 1. This is 0, x squared, 0, 2, y, density function is at kxy, and I'm doing dy dx. So I'm going to kind of clean this up a little bit before I integrate. All right, so I'm going to get kxy squared dy dx. Then I'm ready to integrate. So I'm going to get 1/3 kxy cubed, and we're going from 0 to x squared dx. Okay, so we're still going from 0 to 2. Then I'm going to have 1/3 kx, and I'm going to take this upper limit and plug that in for the y. So I'm going to have x squared cubed dx. Don't have to worry about the bottom limit because that's just 0. All right, so again, you got to clean this up. I have 1/3 k. This would be x to the 6 times another x, would have x to the 7th dx. And then integrate finally again, but this time with respect to x. So I'm going to get 1 over 24 k x to the 8, 8th power. We're going from 0 to 2, and then plug 2 in for the x. That's a 2 there. And then simplify this. So you get 32 thirds k. So that there is your m sub x. That's your moment about the x-axis. Now I'm going to go ahead and find the moment about the y-axis. My function, there's my double integral. These are still the same. All right, so you get this here. You're going to have to clean this up before you can integrate. 0 to 2, 0 to x squared, kx squared y, dy dx. Actually, I kind of made a mistake. Got to switch this over. That should be dy dx. There we go. All right, back on track. So we're going to integrate this with respect to y. So I get 1 half k x squared y squared, going from 0 to x squared dx. Okay, go ahead and plug in the x squared for your y. So I have x squared squared. All right, then you got to clean this up a little bit more. All right, so I've got x to the 4th times x squared. That's x to the 6th. And then finally integrate one more time. I get 1/14 k x to the 7th. I'm going from 0 to 2. Plug 2 in for the x and simplify. So you get 64 over 7k. All right, so that's all you have to do to find the moment about the y-axis. So we found the moments, and now we're going to use these to find the center of mass. All right, so now we want to find the center of mass of a variable density planar lamina. So if m is the mass of a lamina, then the center of mass is given by this here. It's x bar, y bar. It represents averages if you took a statistics class. And basically x bar is going to be the moment about the y-axis divided by x, and y bar is going to be the moment about the x-axis divided by m. Think of it this way. Let's see. Here you have x, y, z. Right, you have some lamina here. Maybe this is the center of mass. For x bar, the moment about the y-axis, right, its tendency to rotate about the y, basically to find the x bar, we have to know how far along the x-axis do we need to move, basically away from the y-axis to stop the lamina from rotating in the about the y-axis. So you would take the moment about the y-axis and divide it basically by the mass of the overall lamina. Basically, the moment about the y divided by the total mass gives us an x value, gives us the distance from the y-axis. And then your y bar, similarly, we have to figure out how far we need to be away from the x-axis to stop this planar lamina from rotating about the x-axis. So you take the moment about the x-axis and divide it by the total mass of the lamina. So that will give us a distance for y, distance along the y-axis or in the y direction. All right, so example 3, or last example, still working with that same lamina, but now we just want to find the center of mass. So we already have all the parts for this problem to complete it. So here's where I'm going to write the solution. X bar, y bar, basically the averages are equal to this here. All right, so from the very first example, we got the mass was 16/3, okay, and we found the moments. The moment about the x-axis, we got that was 32/3 k. The moment about the y-axis, that was, what was that? That was 64/7 k. So you have all the parts. So I'm just going to kind of plug everything in. So the x bar is going to be the 64k divided by 7 over the total mass, which was the 16k divided by 3. And then the y bar was the moment about the x-axis, which was the 32k divided by 3, divided by the mass. All right, and then you have to clean this up. You got 64k divided by 7 times 3 over 16k, 32k divided by 3, oops, that should be there, times 3, 16 over k. And then you can, the k's divide out, some of the other stuff divides out. You clean this up and you're going to get 12/7, 2. So this here is your center of mass, but just check it, make sure it makes sense. So the lamina that we were working with looked like this, right? And 12/7 would put us 12/7 would put us about here, comma 2 would put us like right here. So it's saying that's where the center of mass is. Make sure that, if you go plot your center of mass, it's somewhere, on that lamina. Shouldn't be out here or something. All right, so basically this part is denser than the other part of the lamina. And that's it for this section. So try the homework problems. I didn't give you too many, and then we're done with 4.4.